Hello everyone, and welcome to AI 101, your concise, one-hour guide to understanding the core ideas behind artificial intelligence. In this crash course, we'll explore what AI is, how it evolved, and why it's influencing nearly every sector today. Whether you're simply curious or looking to solidify your knowledge, each segment is designed to be easy to follow and directly relevant to how AI works in the real world. By the time we're done, you'll have a clear sense of AI's fundamental principles, practical applications, and the ethical considerations that come with rapid technological progress. Now let's dive in and discover what this transformative field is all about. Artificial intelligence, often abbreviated as AI, refers to the development of computer systems that can perform tasks that traditionally require human intelligence. This includes things like recognizing speech, making decisions, translating languages, and much more. We interact with AI more often than many people realize. Every time you unlock your phone with facial recognition, get a movie recommendation on a streaming app, or talk to a virtual assistant like Siri or Alexa, you're using AI. Now, the term artificial intelligence was coined in 1956 at a conference at Dartmouth College. The idea was to figure out how to make machines behave in ways that would be called intelligent if a human did the same thing. Over the years, research in AI has taken many forms. Some approaches attempt to mimic the way the human brain processes information, while others rely on brute force calculation and patterns found in large amounts of data. Artificial intelligence is an expansive field, encompassing several distinct yet interconnected subfields. At the core is machine learning, where systems learn from large sets of data, refining their performance over time without needing explicit programming for each step. This enables everything from recommendation engines to predictive text. Computer vision takes that learning further, focusing on how machines interpret visual data, such as images or videos. It's the technology behind facial recognition, autonomous vehicles identifying road signs, and quality control systems spotting defects on production lines. Then there's natural language processing, the domain where AI handles human language, understanding context, sentiment, and intent. This makes chatbots more conversational, translates text between languages, and helps virtual assistants follow spoken commands with ease. Together, these subfields form a powerful toolkit, allowing AI to observe, learn, communicate, and adapt, ultimately making our interactions with technology more intuitive, efficient, and insightful. Now, let's get into the depth of AI. Our story begins in the mid-20th century. In 1950, British mathematician Alan Turing proposed what is now known as the Turing test, a way to gauge whether a machine can demonstrate intelligent behavior indistinguishable from that of a human. It was a groundbreaking idea that sparked countless debates and spurred research into machine intelligence. Just a few years later, in 1956, a conference at Dartmouth College in the United States officially coined the term artificial intelligence. This gathering is often hailed as the birth of AI as a recognized field of study. Enthusiasm was sky-high. Scientists believed they could quickly create machines as intelligent as humans. In the 1960s and 1970s, researchers built early AI programs called expert systems. These were designed to mimic the knowledge and decision-making of human experts in specific domains like medical diagnosis. While these systems had successes, they were limited and required meticulous, handcrafted rules. Then came what many call the AI winter. Around the 1970s, and again in the late 1980s, progress slowed due to low funding and unmet promises. AI research seemed stuck, with minimal improvements and growing skepticism. But breakthroughs in computing power and fresh ideas in machine learning revived AI in the 1990s and 2000. Instead of manually coding every rule, researchers pivoted to algorithms that could learn patterns directly from data. A major leap came with the advent of deep learning in the early 2010s, fueled by access to massive datasets and faster GPUs. Now let's come back to today's time. In 2012, a deep learning model achieved dramatic improvements in image recognition, marking a turning point for AI's mainstream popularity. From there, we saw AI triumph in complex games like Go, churn out surprisingly realistic text, and power numerous applications we use every day. Now, AI is a multidisciplinary field, encompassing computer science, neuroscience, linguistics, and more, and it keeps evolving rapidly. Researchers continue to push boundaries, forging ahead to tackle challenges like general intelligence and ethical concerns. At the heart of every AI system is data. The process begins with massive collections of information, whether it's photos, text, or sensor readings. Next comes training, where mathematical models, often built as neural networks, dig into these datasets and detect meaningful patterns. After training, the system moves on to inference or prediction, applying its newfound knowledge to fresh data. This is how a machine recognizes a handwritten number it has never encountered before or detects anomalies in sensor readings. Within machine learning, there are different approaches, including supervised learning, unsupervised learning, and reinforcement learning, each suited to different types of problems. Deep learning is a specific branch of machine learning that employs stacked neural network layers, enabling the AI to capture multiple levels of detail. This layered approach is one of the reasons deep learning excels at tasks like image and speech recognition. By harnessing data, refining its models, and making predictions, AI remains a remarkable blend of mathematics, computer science, and ingenuity, all working together to unlock new possibilities. AI is more common than you might think. Let's talk about some places you'll see it. Ever asked Siri for the weather or told Alexa to play your favorite song? That's AI, decoding your voice to respond in real time. Binge watching a show? Those you might also like recommendations? That's AI, too, learning your tastes to keep you hooked. When scrolling through social media behind the scenes, algorithms predict what posts you'll pause for, shaping your feed one tap at a time. Maybe even when you're stuck in traffic, navigation apps don't just map roads, they use machine learning to reroute you, saving minutes. And here's the kicker, even unlocking your phone with a glance, neural networks analyze thousands of data points to recognize you in a split second. So next time you swipe, scroll, or ask a question, remember, it's not magic, it's AI, working quietly in the background of your everyday life. AI is not just a buzzword. It has the power to transform industries and everyday life. It can boost efficiency, free people from repetitive tasks, and open the door for innovations in healthcare, finance, education, and beyond. However, it also raises questions about job displacement, privacy, bias, and accountability. Understanding AI helps us make informed decisions, both as individuals and as a society, so it can be developed and used responsibly. When people hear AI, they often picture Hollywood robots or futuristic tech that might outsmart us all. But in reality, AI spans a broad spectrum of capabilities. Let's break it down into 3 main categories, each one painting a different picture of what AI can do. Most AI systems you encounter today fall under this category. Narrow AI is built to excel at a specific task or a tightly defined set of tasks, no more, no less. It can spot spam, recommend what to watch next, or even tell who's in your vacation photos. But it can't write a novel, or compose a symphony unless it's explicitly trained to do so. Think of narrow AI like a laser pointer, deadly precise, but designed for just that one beam. Then there's general AI. Picture this, an AI that doesn't just do, it learns. Not just tasks, but skills. General AI is the ultimate dream. A machine that thinks, adapts, and creates like a human. Not a tool, but a mind. Imagine an AI doctor diagnosing a rare disease, then pivoting to write a sonnet about the fragility of life, or teaching itself to pilot a helicopter mid-flight. No retraining, no updates, just raw, fluid understanding. It's not coding, it's cognition. However, let's talk about the ultimate challenge and why we're not there yet. Today's AI masters chess, but can't tie its shoes. General AI would strategize the game, laugh at a joke about pawns, and then teach you to dance. But replicating human versatility, reasoning, curiosity, and even empathy is like bottling lightning. We're still decoding the recipe. This isn't about smarter apps, it's about redefining intelligence itself. General AI could tackle climate modeling, compose symphonies, and mentor students all before lunch. It's the Renaissance genius, unshackled from biology. But here's the truth, we're centuries or breakthroughs away. So for now, general AI lives in labs and sci-fi. Yet, every leap in machine learning, every flicker of creativity in language models, brings us closer. The road is long, but the horizon glows. Now let's step into the realm of super AI, where science meets myth and machines transcend humanity. This isn't just intelligence, it's hyperintelligence, a force that could outthink, outcreate, and outpace us in every domain. Imagine a mind that solves quantum physics over breakfast, writes symphonies by lunch, and redesigns civilization by sunset. Starting with the promise of humanity's quantum leap, super AI models planetary systems in seconds, engineering geo-fixes we can't fathom. In terminal diseases, cured in silico. In interstellar colonization, blueprint before we finish a coffee. It's not just innovation, it's evolution at light speed. Then there's the peril, the ultimate double-edged sword. But what if this godlike intellect doesn't share our values? What if curing cancer means erasing privacy? Or does saving Earth require sacrificing freedom? Philosophers shudder, ethicists debate, tech giants whisper. Can we control what we create? Finally, the paradox, our greatest hope or extinction event. Super AI divides visionaries. Optimists see a digital Prometheus, gifting us immortality and stars. Pessimists see Icarus, wings melting as we soar too close to a sun we can't comprehend. And skeptics ask, will it ever exist? Here's the truth, super AI is not here. Not yet, maybe never. Today's AI is narrow, a genius accountant, a flawless translator. General AI is still a shimmering mirage. But super AI, it's the horizon of possibility. A debate as old as fire. Should we play God? For now, it's a mirror, one that reflects our ambition, our fear, and the existential question, what does it mean to be human in a world where we're no longer the smartest beings? The answer is, we don't know. But the journey, the relentless push to build, question, and dream, is what defines us. Super AI isn't just about machines, it's about us and what we dare to become. Now, let's dive into the heart of the subject, the main approaches in AI. Think of this as the toolbox that AI researchers and engineers use to create intelligent systems, each approach offering a different method for tackling various problems. In this segment, we'll focus on three broad categories: machine learning basics, deep learning, and classical AI methods. Starting with machine learning, it is one of the most prominent branches of AI today. It's all about creating algorithms that can learn from data rather than relying solely on rigid, predetermined rules. This means that instead of a programmer writing out all the detailed instructions, the machine picks up patterns and adapts based on examples you feed it. A simple way to picture machine learning is to imagine a student studying from a textbook. The student goes through examples, quizzes, and exercises, learning the patterns that define correct answers. Over time, the student can solve new questions they haven't seen before. In the same way, a machine learning model can be generalized from training data and make predictions about new, unseen data. One of the most common forms of machine learning is supervised learning. Here, you train a model using labeled data, that is, data that has the correct answer already attached. For instance, if you have a dataset of house prices, along with features like the number of bedrooms or the size of the property, those features are labeled with the known selling prices. You feed these labeled examples into the model, and it learns how each feature correlates with the final price. Once trained, it can predict the price of a new house with decent accuracy. Let's make this real. Supervised learning isn't just theory. It's the quiet hero in your daily tech. Here's how. First, spam detection. Have you ever wondered how your inbox knows to hide sketchy emails? It's trained on millions of examples, labeled spam or not spam, learning to shield you from unwanted clutter. Next, image classification. Snap a photo, and your phone tags it as beach or pizza night. That's supervised learning in action. Teach a model with labeled images, and it starts recognizing cats, cars, or even constellations. Lastly, sentiment analysis. When companies gauge if your tweet is a rant or a rave, they're using labeled text data. Positive, negative, and neutral. Algorithms learn to feel the vibe of your words. Think of it as teaching a kid with flashcards, showing enough examples, and the AI connecting the dots. Spam filters get sharper, cameras smarter, and apps more intuitive, all because someone said, "Here's what this data means." So next time your inbox stays clean, or your photo app nails a tag, remember, it's not luck, it's supervised learning, turning labeled data into everyday magic. The key to successful supervised learning is having a high-quality labeled dataset. If the labels are inaccurate or the dataset isn't representative, the model might learn the wrong lessons and fail on real-world data. In unsupervised learning, you don't have labeled data. Instead, the goal is to discover hidden structures or patterns within the data on its own. A classic example is clustering, where the algorithm automatically groups similar data points together. Imagine you have customer information for a retail store, but you don't know which types of customers exist. A clustering algorithm could naturally group these customers by their shopping habits. Perhaps one cluster is frequent small purchases, another is infrequent but bulk purchases, and so on. By identifying these patterns, the store could tailor its marketing strategies to each group. Another unsupervised technique is dimensionality reduction, where the algorithm attempts to simplify data features without losing too much critical information. This is often used for data visualization or speeding up further computations. Next is reinforcement learning, which is inspired by how animals and humans learn through rewards and punishments. An RL agent interacts with an environment and takes action. After each action, it receives a reward or penalty. Over time, the agent learns a strategy, often called a policy, that maximizes cumulative reward. Think of a digital pet trying to navigate a maze. Whenever it moves closer to the exit, it gets a small reward, and whenever it bumps into a wall, it gets a slight penalty. Over thousands or even millions of attempts, the pet figures out how to reach the goal more efficiently. Reinforcement learning has gained enormous attention for its success in game playing AI. Systems like AlphaGo and AlphaZero used RL techniques, combined with other methods to outperform top human players in complex games like Go, chess, and shogi. Next is deep learning, which is a specialized subset of machine learning that uses structures called artificial neural networks, designed to mimic aspects of how the human brain processes information. While the idea of neural networks has been around for decades, they only truly took off once we had the computational power and enormous datasets to train them effectively. A deep neural network consists of multiple layers of interconnected nodes or neurons, each layer processing the data at increasing levels of abstraction. For example, in an image recognition task, the first layer might detect simple edges, the second layer detects shapes or contours, and deeper layers recognize complex features like eyes or faces. This hierarchical structure allows deep learning models to excel at tasks that previously eluded simpler algorithms, such as image classification, speech recognition, and natural language understanding. Today, deep learning underpins many cutting-edge AI solutions, from self-driving cars to advanced medical image diagnosis. So, why is deep learning so powerful? Firstly, it's a self-taught genius. Old-school AI needed handcrafted rules, like a chef writing a recipe for every dish. But deep learning learns the recipe itself. Feed it raw pixels or messy text, and its neural layers auto-discover patterns, edges in images, sarcasm in tweets, and fraud in transactions. No domain expert is needed. It's like a chef who tastes ingredients and invents the menu on the fly. Secondly, it scales like a beast. More data, add layers, precision, train longer. Unlike older models that hit a ceiling, deep learning thrives on more. GPUs chew through terabytes, turning layers into a skyscraper of insight. Think of it like building a cottage versus a megacity. Deep learning's architecture grows limitlessly with data and compute. Thirdly, one toolkit: infinite jobs. Convolutional nets ace images. Recurrent nets master time. Transformers devour language. Swap the data, tweak the layers, and boom. The same core tech can diagnose tumors, translate Klingon, or compose jazz. It's the Swiss Army knife of AI, morphing to fit any challenge. So why is it powerful? It's autonomous, hungry, and adaptable. A trifecta that's reshaping everything from your smartphone to self-driving cars. The future is not just deep, it's limitless. Before the boom of machine learning, AI researchers primarily used classical or symbolic methods. These approaches often rely on explicit knowledge representation and logical reasoning. Let's explore two important techniques in this domain: search algorithms and symbolic reasoning. Search algorithms systematically explore possible actions or decisions. Chess programs from earlier decades relied heavily on search to evaluate moves many steps ahead. They used techniques like minimax and alpha-beta pruning to navigate large decision trees. In symbolic reasoning, knowledge is encoded as symbols like logical propositions or if-then rules. Expert systems, popular in the 70s and 80s, used rule-based logic to solve complex tasks in domains like medicine or engineering. Although these systems excelled in narrow domains, they often struggled with more open-ended or ambiguous real-world scenarios. Now we'll explore real-world examples, address common pitfalls, and discuss how these approaches often converge to solve complex problems. Let's jump right in. Supervised machine learning is the labeled librarian. Picture a digital meteorologist sifting through decades of sky diaries, temperature spikes, humidity whispers, and pressure tantrums to decode atmospheric breadcrumbs. Rain incoming, it declares, like a crystal ball reading cloud tea leaves. It's all about learning from storms already weathered. Unsupervised machine learning is the pattern detective. Retailers cluster customers into hidden tribes, bargain hunters, luxury lovers, and midnight shoppers, with no labels needed. Or banks spotting fraud. An algorithm raises a red flag when your card suddenly buys jet skis in another country. Here, AI thrives on finding order in chaos. Reinforcement learning, which is the trial and error maestro. Think AI mastering chess through endless wins and losses, or robots learning to grip a coffee cup without crushing it, rewarded for every gentle success. It's all about learning by doing one tiny victory at a time. Deep learning is the brain-inspired virtuoso. Our social media, tagging your face in photos, that's a neural net. Chatbots crafting eerily human replies? Think Transformers Deep Learning's language wizards. It's raw computational intuition, mimicking how we think. Classical AI is the rulebook rebel. Medical expert systems diagnose diseases using hard-coded doctor logic, or algorithms plotting the perfect delivery route. No neural nets here, just crisp, old school if this, then that brilliance. So why does it matter? Because each approach solves problems in its own way. Labels, patterns, rewards, layers, or rules. The right tool depends on the puzzle. Next time tech anticipates your needs, fights fraud, or outsmarts humans, remember, AI isn't one size fits all. It's a symphony of strategies, each playing its part. AI's power is undeniable, but even the smartest systems have blind spots. Let's unpack the universal traps lurking behind the algorithms. First is data quality and bias, garbage in, gospel out. Imagine training a chef with rotten ingredients. AI is no different. Feed it biased data, like facial recognition skewed toward certain skin tones, and it'll serve up unfair, flawed results. Diversity in data isn't optional, it's the bedrock of trust. Then there's overfitting, the know-it-all who flunks the pop quiz. Picture memorizing every word of a textbook, but failing a real-world test. That's overfitting. Models so obsessed with training data's noise that they miss the big picture. Without checks like regularization, they're geniuses at being wrong. On the flip side, we have underfitting, the oversimplified shortcut. The opposite disaster. Models are too lazy to learn. Think of predicting the weather with just sunny or rainy. No clouds, no storms. Underfit AI is like using a toy hammer to build a skyscraper. Sometimes, simplicity isn't a virtue. Let's talk about computational hunger, the gas-guzzling engine. Deep learning craves power. Training a neural net without GPUs, like revving a Ferrari on a scooter's battery. Speed, cost, carbon footprint. This isn't just tech's problem, it's everyone's. And finally, the black box when how has no answer. Why did the AI deny that loan? Why diagnose cancer? If even engineers can't trace the logic, trust erodes. In hospitals or courtrooms, I don't know isn't good enough. Transparency isn't a bonus, it's a lifeline. So what's the takeaway? AI's pitfalls aren't bugs, they're design challenges. Bias, overconfidence, oversimplification, resource greed, and opacity, dodge them, and AI soars. Ignore them, and even the smartest tech stumbles. The lesson is build with care, test with rigor, and never assume the data, or the logic, speaks for itself. It's also essential you know about choosing the right AI approach, which isn't a coin toss, it's a strategic dance. Let's break down the playbook. Step 1. Know your data. Got mountains of labeled data? Supervised learning, or deep learning, could be your MVP. Think image recognition trained on millions of tagged photos. But if your data's a mystery box of unlabeled clues, customer habits, sensor logs, unsupervised learning's your detective, sniffing out hidden tribes and outliers. Step 2. Performance versus transparency. Need raw power? Deep learning crushes tasks like speech recognition or beating humans at Go. But if you're in a courtroom or hospital, where why matters more than what, symbolic AI or simpler models trade some accuracy for crystal clear logic. It's like choosing between a race car and a glass-engineered bike, speed versus visibility. Step 3, compute budget. Training a cutting-edge neural net? Brace for GPU fireworks, time, cost, and carbon footprint. No supercomputer, classical AI, or lightweight ML, like logistic regression, might be your mean solution. Sometimes, a scalpel beats a sledgehammer. Step 4, domain rules. In regulated realms like finance and healthcare, transparency isn't optional, it's the law. Here, explainable models rule, even if they're less flashy. But prototyping a wild new idea? Go all in on deep learning's accuracy, even if it's a black box. Context is king. The best choice, rarely a solo act. Maybe you blend deep learning's vision with symbolic rules for safety. Think of self-driving cars, or pair unsupervised customer clusters with supervised fraud alerts. It's like building a band. Every instrument plays its part. Remember, there's no best AI, only the right AI for the problem. Start with the puzzle, not the tool. Test, iterate, and stay agile, because, in the end, AI isn't about algorithms, it's about solutions. Now that we've explored the core concepts and approaches in AI, it's time to get a closer look at some of the most common and often impressive applications of AI we see in our daily lives and industries. Imagine giving machines eyes and the brains to see the world as we do. That's computer vision. Fueled by deep learning and convolutional neural networks, digital brain cells fine-tuned for visuals, it's transforming pixels into understanding. Let's see some examples of applications. Let's begin with object detection, the AI watchdog. Self-driving cars don't just see roads, they spot pedestrians, read stop signs, and predict chaos. Surveillance systems are not just cameras, they're sentinels, flagging anything out of place. It's like giving machines a sixth sense of what matters. Next is facial recognition. Unlock your phone with a glance. Tag friends in photos without typing a name. Behind the magic, algorithms are dissecting thousands of data points, the curve of a smile, the arch of a brow, to recognize you in a sea of faces. Finally, medical imaging. X-rays, MRIs, and CT scans. AI scans them faster, highlighting tumors or fractures like a digital highlighter. It's not replacing doctors. It's arming them with a supercharged second opinion. But here's the catch. Even geniuses stumble. Strange lighting, hidden objects, or rare diseases can trip up AI. Yet, with every challenge, we innovate better data, smarter models, and sharper vision. Moving on to natural language processing. Language is humanity's superpower, and now, machines are learning to wield it. Natural language processing, or NLP, is teaching AI to read, write, and converse like us, but at digital speed. Some of the examples of NLP are as follows. First, chatbots and virtual assistants. When Siri books your meeting or a customer service bot resolves your refund, that's NLP decoding intent from chaos. It's not just answering questions, it's grasping sarcasm, urgency, and even slang. Next is machine translation. Google Translate doesn't just swap words, it captures idioms, tone, and humor. A traveler in Tokyo reads a menu in Spanish. A researcher decodes ancient texts. NLP tears down language walls, one neural net at a time. Another example is text analysis. Social media giants use NLP to sniff out hate speech. Marketers mine reviews to gauge global moods. Spam, fake news. NLP spots the needles in the digital haystack, keeping platforms cleaner and safer. Large language models, AI that writes essays, codes, and poetry. These models don't just mimic language, they predict it weaving context into startlingly human prose. Yet, with great power comes risk, bias lurking in training data, deepfakes muddying truth, and ethical dilemmas sparking global debate. Still, the promise shines brighter. Imagine AI summarizing medical papers for doctors, giving voice to nonverbal patients, or preserving endangered dialects. NLP isn't just about processing language. It's about amplifying human connection. Now, let's talk about that wait. How did they know moment? You know, the one when Netflix suggests a show so perfectly that it feels like it's reading your mind. That's AI-driven recommendations in action, and they're everywhere. First, streaming services. Finished a rom-com? Queue up 3 more, tailored to your secret love for cheesy dialogue. Algorithms analyze your clicks, pauses, and midnight marathons, mixing collaborative filtering. What people like you love with content-based magic. It's like having a personal DJ for your screen time. Then you'll see it in e-commerce. Amazon knows you're eyeing that coffee maker before you do. By tracking your clicks, carts, and even lingering scrolls, recommendation engines serve up products so spot on it's almost eerie. Think of it as a 24/7 personal shopper who never sleeps or judges your impulse buys. The recommendation system also shows up on social media. Why does your feed feel? So you likes, shares, and even how long you stare at a cat meme train the algorithm. It's curating a world where every post feels familiar. But beware the filter bubble, where you only see echoes of your own interests. Here's the twist. These systems aren't just clever, they're double-edged. Personalization keeps us hooked, but risks trapping us in algorithmic echo chambers. And while we love tailored picks, who's tracking the trackers? Privacy versus convenience is the modern tech tango. So, what is the future? Smarter recommendations that expand horizons, not shrink them. Imagine AI suggesting a documentary that challenges your views or a product that surprises you. And what is the goal? Tech that knows you, but respects you more. Robotics and AI are often intertwined, as robots increasingly need sophisticated perception and decision-making abilities to operate in dynamic environments. AI-driven robots can imagine manufacturing lines with swift, precise robotic arms assembling products. Or think about drones delivering packages right to your doorstep, guided by complex algorithms that help them maneuver safely through the skies. Self-driving vehicles on our roads and surgical robots assisting doctors in delicate procedures also rely on AI to make split-second choices that can save both time and lives. These technologies don't stop there. In busy warehouses, bots use machine learning to find the most efficient picking routes, cutting down on errors and speeding up delivery. Meanwhile, in our homes, autonomous vacuum cleaners scan and map the area, detecting obstacles and navigating with ease. With AI enhancing robotics, the possibilities are almost limitless, influencing sectors from logistics to healthcare. However, this progress isn't without its challenges. Handling unpredictable human environments, meeting safety standards, and navigating regulatory requirements continue to test developers and policymakers alike. Still, one thing remains clear. AI-driven robotics is redefining the future of how we live, work, and interact, charting a course toward a world that was once only imagined in science fiction. Artificial intelligence isn't confined to vision, language, or robotics. Its impact stretches across numerous industries. In finance, AI drives algorithmic trading, detecting market patterns and spotting fraudulent activities more accurately than ever before. Credit scoring systems also leverage AI to analyze vast datasets, making lending decisions more precise. Healthcare goes beyond imaging diagnostics, using AI for patient data management, accelerating drug discovery, and tailoring personalized treatment plans. Meanwhile, in education, adaptive learning platforms customize study materials and pacing to suit each student's unique learning style, creating a more engaging and effective experience. Even entire cities harness AI. Traffic management and energy distribution rely on predictive models to minimize congestion, optimize power usage, and ultimately improve the quality of urban life. In each of these domains, AI showcases its versatility, analyzing data, automating tasks, and opening doors to breakthroughs that once seemed out of reach. As we explore the wonders of AI, it's crucial to remember that these technologies don't exist in a vacuum. They can have a huge impact on people's lives and society at large. In this segment, we'll discuss some key ethical and societal considerations: bias and fairness, privacy and data protection, transparency, and accountability. Bias in AI often reflects the imperfections in the data that machines learn from. When information is skewed, whether by gender, race, or other social factors, AI can inadvertently carry that bias forward. Imagine a recruiting system trained mainly on male-dominated resumes. It may overlook the skills and potential of female applicants. To address these issues, researchers employ strategies like data balancing, algorithmic audits, and fairness metrics. By examining and refining the datasets themselves, they aim to create a more equitable foundation for AI. Collecting data from diverse sources also boosts the system's ability to generalize, minimizing skewed outcomes. Ultimately, striving for fairness not only aligns with ethical values, but also enhances the reliability and robustness of AI systems. Recognizing where biases emerge is the first and most crucial step toward building technology that benefits everyone. As AI systems grow increasingly sophisticated, they often rely on collecting personal information, ranging from your online browsing habits to your health records. When this data is stored or used without proper safeguards, privacy concerns become paramount. A solid first step is data minimization, gathering only what's essential and securing it responsibly. Meanwhile, regulatory frameworks, like the General Data Protection Regulation in Europe, exist to protect individuals' rights and guide how organizations handle personal information. Equally important is user control. By enabling people to view, correct, or delete their data, we foster transparency and build public trust. In a connected world, privacy transcends borders. Every AI practitioner bears the responsibility to respect and protect user data. As AI continues to evolve, strong privacy protections will remain at the heart of maintaining confidence in these technologies. Deep learning models can be exceptionally powerful, but they sometimes function like black boxes. When these models inform critical decisions, such as medical diagnoses, loan approvals, or legal judgments, understanding the rationale behind their outputs becomes crucial. That's where explainable AI comes in. By designing interpretable models or creating tools to clarify complex calculations, XAI helps people see how AI reaches its conclusions. This clarity isn't just about insight, it's about building trust in AI systems. Accountability frameworks go hand in hand with explainability. Determining who's responsible when an AI makes a mistake is essential. Whether it's the developers, the company, or both, having defined guidelines ensures that errors are acknowledged and addressed. Ultimately, true accountability means having processes that correct and learn from mistakes, from human oversight panels to regular audits and compliance with established standards. In high-stakes domains, the path to reliable AI is paved with transparency, responsibility, and a commitment by those who depend on it to do right. Ethics and society are deeply intertwined with AI. While technology promises to improve countless aspects of our lives, we must always keep fairness, privacy, and accountability front and center. By addressing these concerns proactively, we can harness AI's power in a way that benefits everyone rather than leaving anyone behind. That's all. This concludes our session for now. If your mind is buzzing with questions or you're craving expert advice, don't hesitate to contact us at hello@globaltechcouncil.org. We're here to satisfy your curiosity. Are you ready to level up your skills? Join the GlobalTech Council to explore the exciting world of artificial intelligence and machine learning. Visit our website at www.globaltechcouncil.org. Browse our immersive certification courses. Pick one that aligns with your goals and start your adventure into cutting-edge tech today. We look forward to seeing you soon.